Hello, it's Mr. Norris. This is going to be a test video for the purpose of testing out some new software that I have on my computer that I'll hopefully be able to use in the 2014-2015 school year at PLC. So if you are a teacher and you're watching this, I'm using a software called Screencast-O-Matic. There is a free version and there is a $15 a year version. I am stealing a subscription from another friend in DPS. It's pretty nice software. It allows you to record whatever's on your screen and talk at the same time. So the way I've set up my screen, I have my objectives, and what I'm going to do is my guided notes on the right-hand side of the page, and I'm using a geometry software. It's freeware, so you can just get it directly offline without paying any money, and it's called CPMP Tools, Core Plus Tools, basically. So the purpose of this lesson is going to be to sort of pin down what we mean by rigid motions. We're going to try and take shapes and we're going to try and move them in a graph. We're going to try and move them across a plane. And we're going to try and recognize how we can identify those movements and what kind of vocabulary we can use to explain them. And we're going to try and recognize patterns in ordered pairs. So if I take a point from one part of the graph, how is it going to change when I perform some kind of motion upon it? So let's go ahead and start out by constructing a triangle in the plane. So I'm going to pause for a second and construct a triangle in the plane. Okay, so I now have a triangle. That triangle we're going to call PQR. So it's going to be triangle PQR, and we're going to be working with this triangle throughout this lesson. So we're going to try and perform a reflection on it, a rotation, as well as a transformation. So let's go ahead and get our general points. Now, as far as vocabulary goes, what I've done is I figured out what my ordered pairs are. 4, 2, 2, 7, and 1, 2 are called ordered pairs. I'm going to go ahead and include that in my vocabulary list. So ordered pairs. Can you think about a way to describe that? If you're trying to tell somebody what an ordered pair is, maybe you could call it a point. I'm going to try and be a little bit more precise. I'm going to say some point xy in the plane. And by the plane, I mean a graph that we're talking about. Okay, so now what I want to do, I don't know why that's highlighted. Now what I want to do is I want to be able to think about reflections. So I'm going to go ahead and I tell the computer that I want to worry about this triangle. What I've indicated in red, that's the triangle that I'm thinking about. And I'm going to tell the computer that I want to perform a reflection on this. So I'm going to say reflect object, and I think I want it to reflect through this y-axis. Okay? So I've taken this this triangle on the right-hand side, and I'm thinking about flipping it across the y-axis. Okay? Not too bad. So let's figure out what that did to the points. So I was at P 1, 2. What do you think would happen as we're going from P in this part of the graph to P in this part of the graph, from right-hand side to left-hand side? What changes with the x-coordinate? Well, think about it as when you're imagining points, whenever you're in this side of the graph, your x is always positive and your y is always positive. But when you go to this side of the graph, your x is negative, but your y is still positive. So when I went from the triangle on the right to the triangle on the left, I changed the fact that I'm going from a positive x to a negative x. But my y-coordinate kept the same size. So sometimes in the problems that you're going to be given, you're going to be asked for a general rule. In other words, if I give you any point x, y, and I don't care what it is, I can choose any point that I want. What is it going to become under this transformation? Well, I know that my x changes signs, so if I have an x, that's going to become negative x, and my y stays the same because I went from 2 to 2, so there's a y that stayed the same. I went from 7 to 7, there's a y that stayed the same. So I'm going to go from x comma y to negative x comma y. This is called my general rule. So we've learned a little bit about ordered pairs as they relate to reflection. So let's come back over here to this window. So now I'm going to think about changing, oops, beg your pardon, my software was acting a bit finicky, so I had to restart it. But I'm back, and I'm back to where I reflected this triangle. The only difference that I want to point out is before the program shut down, we were looking at triangle PQR, and now that I've opened back up, we're looking at triangle ABC. Not too big of a change, but I wanted to point that out. Okay, so let's imagine that we were originally thinking about a reflection across the y-axis. But the reality is we can pick any line of symmetry that we want. So maybe I want to reflect it across this line. Okay, so now I'm reflecting across the line y equals 1. Now I'm back to the y-axis. Maybe I even have that axis of symmetry going through the pre-image itself. That's perfectly fine. So the main idea is not yet to fully understand how every single reflection works, because it's hard to think about what that would look like for every circumstance. But I do want you to recognize that the image is totally dependent upon the axis of reflection, or the axis of symmetry, that we're talking about. So let's go back up to our vocabulary and see if there's anything we need to point out. So we can think about a reflection as a flip, but a flip across what? Well, we have to talk about the axis of symmetry. And I'm going to put slash reflection because sometimes we refer to it that way. So this is not a precise mathematical definition, flip, but sometimes it's just a good way to remember in general what we're doing here. So we're talking about some kind of a flip, and that flip is dependent upon the axis of symmetry, or the axis of reflection. Okay, so I also recognize that in that demonstration I talked about the pre-image, and then I talked about the image. Okay, so the pre-image is the figure before we talk about some kind of transformation. The image is the figure after we talk about some kind of transformation. And of course I can spell, right? Okay, so if you hear me using those words pre-image and image, that is something that you want to consider. Oops, let me go ahead and bring that back. Okay, so now we're going to go back to our original triangle on the left-hand side of the screen, and we're going to talk about a rotation now. In most cases, we are going to rotate around the center. I mean, this point right here, 0, 0. We also sometimes call that the origin. Okay, so I'm going to indicate that I want to worry about this triangle, and I want to do some kind of a rotation. Okay, so maybe I rotate it 90 degrees, or about that, to, let's say, counterclockwise. Okay, so I've done that. I can also tell the computer that I want to rotate it any number of degrees. So maybe now I want to take this and move it down 180 degrees. Maybe I want to take it and move it 270 degrees. Now when you're thinking about this by hand, it's easiest to think about rotations in movements of 90 degrees. So I'm going to leave you with a task, and it's if I have point A, point B, and point C, what's going to happen when I take some x, y, and rotate it 90 degrees counterclockwise? What's going to go in that space? So I want a general rule for a 90-degree counterclockwise rotation. That's going to be your task. So again, I'm going to take that, I'm going to move it back up here to 90 degrees so you know what it is I'm talking about. So if you look at this as the image, if you look at this as the pre-image, and at this is the image, what's the general rule that we're talking about? Okay, I'm going to leave that. You can think about that as some kind of a turn, and we have to talk about the center, the number of degrees, and whether we're going counterclockwise or we're just going clockwise. Translation is perhaps the easiest, let me go ahead and remove these actually. It's perhaps the easiest kind of transformation that we'll do. So think about walking in a city. You talk about the number of blocks you go, maybe north or south, and then you talk about the number of blocks that you go east or west. Okay? You do sort of the same thing when you're talking about a translation. So I've told the computer that I want to go, let's say I want to go 3 places down, so I put in -3, and, excuse me, 3 places left, so I put in -3, and then I want to go, let's say 2 spaces up. So the computer takes every point in this pre-image in the original triangle in red, and it takes it 3 places to the left, and it takes it 2 places up. I have some x comma y, and I'm taking it, I believe we said 3 places to the left, so I go 3 places to the left, x minus 3, then I go 2 places up, so I do y plus 2. When I think about a translation, I can think about how many spaces I'm going up and down and left and right. So up, down, left, right, and I'm talking about some kind of a slide. So if you're thinking about the simplest way to think about a reflection, a rotation, and a translation, a reflection is a flip, a rotation is a turn, and a translation is some kind of slide. Well, what do we ultimately mean by rigid motions? This entire lesson was about rigid motions. What do you notice about this triangle in the pre-image? So triangle ABC, and this new triangle, triangle A prime, B prime, C prime. So we're talking about two images that are congruent. So in a rigid motion, the pre-image is congruent. So the pre-image stays congruent to the image. We're not stretching these triangles, we're not shrinking these triangles, no matter how we move them in the plane, they're ultimately staying the same shape and the same size. And that's what you have to think about in general terms when you're talking about congruence. When you talk about congruence, we talk about same shape and same size. So we're ultimately going to work more with rigid motions, and we're going to learn about different kinds of motions beyond simply motions that preserve congruence. Remember that we've talked about reflections, rotations, and transformations, and we've identified patterns in the ordered pairs of pre-image and image.